So this is the lecture for mathematical modeling for all the chemical engineers. So let's begin. So as far as the mathematical modeling is concerned, it's very important for chemical engineer, right? So suppose let me begin with, suppose you have given a feed of mixture and you want to separate it, right? So this is suppose a feed of mixture feed, that is liquid mixture, right? Now you are using distillation column. So in the distillation column you are feeding this mixture, and with the help of temperature gradient, because the mixture will have the component of different boiling point, so you will establish temperature gradient along the distillation column, and based on that, at different stage of the column you will separate out, draw the products at the different stages. Okay, so and to quantify how much product you have to draw, you are drawing, you use the thermodynamics, right? As well as fluid mechanics you also can use, because mixing is the process. Mixture, you need mixing and then heating up, converting it into vapor. So two phase liquid vapor multi-phase flow system, you can use here the fluid mechanics. All right, now as far as chemical engineering is concerned, you have to design the process. Now you can do the experiment, and you can do the experiment at pilot scale to design and scale up. Now you can use at different stage of different stage, like advanced, you can use advanced simulator like aspen, ansys, fluent, HYSYS, star cd, camshaw. So these aspen and ansys, fluent are different scales. Okay, so you use these advanced simulator to get the solution. Now how do you conceptualize the uh, model? Okay, so suppose you have given a physical word like chemical process plant, and you can model it by two ways, like conceptual modeling based on thought experiment. Okay, like you are using conservation laws, thought experiment based on thought experiment, and empirical observation based on physical experiment you are doing, like you are getting the rate of any reaction. So you will get the discrete data point, concentration and time, then you will plot the curve like between the concentration and time, and then you will get some you will get different data point, and through curve fitting you will get this curve, and then slope to this curve dc or dt will give you the rate. Okay, so this is the empirical observation. Now conceptual modeling means conservation laws as well as the empirical model, you will combine both conservation laws and empirical observations, you will combine both, then you will get the mathematical model. Now as you know that this conceptual modeling, conservation laws, this is also approximation, and empirical observation, when you do the experiment you also make some assumption, right? So this is also approximate. Now if you combine, then you will get the mathematical model, that is also approximate. So this is the but this is the approximation to the physical world. Okay, now this is also complicated, so you will approximate further this mathematical model, and you will get the numerical model that you can solve on the computer, right? So this mathematical model, types of mathematical modeling, this can be divided into various groups like linear and non-linear model. Okay, so linear model, non-linear model, suppose we have a data points and you are getting between data points linear line, then the linear, otherwise non-linear model. Suppose you have the variable, any variable like concentration, and if it appears like e ki power c concentration, okay, or c is square, so this is non-linear type variation, means exponential or transcendental functions and all those. Now steady state versus dynamic. The steady means with respect to time variable is not changing, and any parameter is not changing, steady state, and dynamic is if with respect to time it is changing. So you will get steady state versus dynamic. You will can get based on that algebraic equations, set of algebraic equations, or ordinary differential equations, or partial differential equation. Now when we will get algebraic equation, when we will get ODEs, when we will get PDs, so the notion of this will give you the notion of lumped versus distributed model. Now model could be lumped, means variable of interest if has no spatial variation, means suppose you are taking a reactor, then concentration of any reactant in the reactor, or anything in the reactor will be same everywhere in the reactor. So it has no spatial variation, so this is lumped. Okay, and distributed means it will have the spatial variation, like concentration is changing at different points in the reactor. Okay, so this is lumped versus mm, distributed. Okay, now this lumped model could be like well mixed reactor, where composition is uniform, concentration is same with respect to space variable, but it could change also. It concentration is same at different point, but it may change with respect to time. If it is changing with respect to time, then this is lumped dynamic model. If it is not changing with respect to time, then lumped steady state model. Now I am giving some examples to find out linear nonlinear model, or steady versus dynamic model, or distributed versus lumped model. Okay, so this is the first example. We are taking steady state, lumped, and linear model. So suppose this is, we have the process flow sheet of methylene production. So this is the reactor, and we are using as reactant, carbon monoxide, CO and S2, and we are getting CH3OH, right? So we are feeding it into the reactant, but you can see the you can see the you know you can see the conversion is very low. So conversion is very low, so you will pass it through the condenser, CH3OH, you will draw some CH3OH and recycle rest, so that you will get higher yield. Okay, so you can use the balance laws. One is around this reactor, and other is around hole. Okay, so inner loop and outer loop, that is, you can apply the balance for C hydrogen as well as for oxygen. Okay, so you are using the balance, different balance equations. You are applying the balance equation. So balance you are applying on the inner loop. So suppose this is C valence. So this is C valence. Okay, so this is C valence, means x mole per minute. This is in, plus this 0. This is out 0.3 0.302 0.302. This is recycling, that is also input in this around the reactor. You are applying the mass balance. So for C, and the in is x mole per minute, and C is coming from here also, so there is CCO and in CS3OS. So 0.302 and 0.004 multiplied by recycle rate mole per minute. So this give you 200. Out is something this F. So F275, and C is here CO and CS3OS. There is no C in S2, right? So 0.274 plus 0.095 multiplied by F. This is the first equation, and this will lead to equation 1. And if you simplify, right, so and then S2 balance if you apply, so S2 means y, and through recycling you will get 0.694, and EH also here, but HCS3OH means H4 means 2 mole of S2, so 0.004 multiplied by 2, and R, so this is something R multiplied by Y plus R. This is in 0.694 plus 0.008 is equal to 275 multiplied by 0.631 plus 2 multiplied by 0.095. So this is the H2 balance, because this is the right hand side you are getting out. So out S2 is this 0.631 and out S2 is 2 moles of H2, so 2 multiplied by 0.095 and multiplied by the flow rate is 275, right? And O valence, if you apply, then O here x plus, and R you are getting from, so O is in CO and O is in CS3OH. So 0.302 plus 0.004 multiplied by R. So this is this, and is equal to 275 multiplied by out means 275 multiply this 0.274 plus 0.095 multiplied by f is 275, right? So this is, if you simplify x plus, you get x plus 0.306, r is equal to 101.475. so you see this equation 1 and this equation 3 is same, so same equation 1 and 3, so you get effectively only two equations. So that's where the concept of linear independence will come. So three equation, but only two are linear independent. So we will later see, we will develop later algorithm for testing linear independence, right? Now for outer loop, similarly, if you apply C valence, then this outer loop, that is this green color, you see the outer loop. So if you apply C for the x, and C is coming CS3OH, means x is equal to P. And for H, if you see, then for H, this is S2. For S2, Y is equal to here H4, so 2 moles of S2, so 2P. X is equal to 2 feet, so 2 more equation, Y is equal to 2P, so 2 more equations you will get. But you see that X is equal to 2P, so minus 2x plus Y, if you add up, this will give you 0. Because x and p is related, so if you will get the value of x, you will get the value of p, and you will also get by multiplying by 2, you will get the value of y. So these are related, so I have converted it into single equation. So first we write it these 5 equations in the matrix form, so we have written it, but recall, but understand that equation 1 and equation 3 are same, so we can eliminate that. Moreover, this equation 4 and equation 5, we can combine it into minus 2x plus y is equal to 0. So we will get only 3 equations and 3 unknowns, x, y, r. See, in this system, x, y are unknown, and this is x, y, and recycle rate, this is unknown. Okay, p can get based on, if we will get value of x, then p will be same as x through equation 4, and y is equal to 2p, p is, or y by 2 is equal to p. So either you get x or you will get y, you will get the value of p. Alright, so 3 equation and 3 unknowns. Now here comes the linear algebra, right? So you can solve this into the MATLAB, you can develop the code for MATLAB. So here you can use the Gauss elimination, that are direct method, and in some cases we use the iterative methods. Okay, so direct method and iterative method. So here the whole of either you solve differential equation, partial differential equation, you will ultimately ends up with the simultaneous linear equation. Even non-linear equation you will get, then you will linearize and you will get a simultaneous linear equation, and you will have to solve simultaneous linear equation. So you have to develop the algorithm for how to solve these simultaneous linear equation. Means linear algebra is important for mathematical modeling. Okay, so we will discuss it later. Now another example, but we are taking multi-component plasma. Here this is a steady state lumped but non-linear equation. So this is what is multi-component plasma. So suppose you are feeding some mixtures having composition T, Zi, and temperature Tf and Vf, and this is the drum where we are putting this feed, and we control its composition, so it gives top product vapor and bottom product liquid. So liquid composition xi and yi, it will be separated out, but liquid and vapor, and we can control its composition through temperature, and by controlling its drum temperature and pressure. Okay, so there is a the unknowns are temperature and pressure and psi, vapor fraction. Okay, so you can use the mass balance laws plus phenomenological model, model, and you will get the Rice S4 equation, that is sigma I is equal to 1 into n 1 minus ki zi divided by ki minus 1 psi plus 1. Ki is nothing but the you will get from thermodynamics, that is the equilibrium ratios, right? Now this is the equation. Now this equation you will get. Now suppose if psi is equal to 0 means vapor fraction is 0. So what is vapor? Psi is equal to 0 means this is the, what is psi? Psi is fraction of feed in the vapor. If psi is 0 and suppose this drum is at atmospheric pressure, then what is the temperature? What we will call the temperature? Okay, so this is imagine that you don't have the vapor fraction, so you have the liquid mixture only. Okay, this is the liquid mixture and you are heating it at the atmospheric pressure, so you got the first bubble. So that kind of interpretation. So this is nothing but the bubble point size equal to 0. Similarly, if you put size equal to 1, you will get the dew point. So this single equation reflects into bubble point and dew point calculation as well. Okay, and similarly, if T is known and P is unknown, you can calculate bubble point pressure, dew point pressure. So bubble point, dew point, all calculation you can do this with this single equation. Now another example that we are taking is liquid. This is suppose different stages and 1 2 3, and we are liquid is flowing in this way and vapor is flowing in this way in the counter current wise, and x1 x0 x1 x2 x3 are the composition of liquid, and y1 y2 y3 y4 is the composition of vapor. Now here the nomenclature of the variable is like this. So any stage, the leaving components, leaving compositions have the same subscript. Okay, so stream leaving the leaving the stage carry the same index, like x2 means leaving stage 2, liquid composition leaving stage 2, y2 vapor composition leaving stage 2. So L is the liquid feed rate and V is the vapor feed rate, right? So how will you develop model for this? Okay, the development state variables are, you know, all x, x0, x1, x2, x3, and all y's, y1, y1, y2, y3, y4, and L and B. These are the state variables in the problem. But this L and B is constant throughout every stage. Under what assumptions? Okay, so if there is no significant material transfer between the two phases, you can assume that L and B are constant. But if there is a significant transfer of material from L to B, then we cannot take L and B are constant, so we will have to take L1, L2, L3, L4, B1, similarly V1, V2, V3, V4. Okay, so that basically solve, you can solve by with the help of Aspen. Okay, you can use the Aspen. Now the second question, is it lumped or distributed? So lumped, we can consider here lumped at every stage. Lumped or distributed means state of mixing. So suppose this is well mixed, then we can take it lumped model, or you can see later on that you can relax this assumption of lumped through by the use of CFD, computational fluid dynamics. Like you can do this. Okay, so this lumped model could be a cause of problem. Okay, so what can we say about exit concentration? So non-linear it could be. So linear equation and non-linear equation. So non-linearity basically comes from thermodynamics, reaction kinetics, and fluid mechanics. Now you will apply the mass balances and at every stages, and one equation you will get for each stage for the mass balance, and another equation you will get from thermodynamics equilibrium relationship, right? So you will get like this. So mass balance at stage 1, you will have the change in composition of the vapor must be equal to the change in composition in the liquid. So whatever increase or decrease in vapor content must be equal to the decrease or increase in liquid concentration. So y2 minus y1, x1 minus x2 multiplied by vapor flow rate here and liquid flow rate here. Similarly for stage 2 you can write similarly for stage 3. You have 3 equations. Now y and x are related because you know at this stage y2 and x2, y2 and x2 is the liquid composition leaving the stage 2, and y2 is the vapor composition leaving the stage 2. Both will be in equilibrium, so they will be related through y is equal to kx. Okay, So y is equal to kx. So y is equal to kx, and let define new variable. Define new variable s is equal to l by kv. So if k will vary, okay, then s will vary, otherwise s will be constant. Means l by kv means you are dividing l here, so you are dividing both sides by kv. Okay, so you will can convert it into this form. You will get 3 by 3, this matrix form, condensed matrix vector form equation you will get like this. Okay, so on the right hand side you will get the forcing function, means x0 is the inlet concentration, that is known, and y4 is also inlet vapor concentration, that is also known on this side. Okay, and liquid concentration. So these are the known quantities on the right hand side, and this is unknown. And you will be having here this is s is known. If l and b you know, liquid flow rate and vapor flow rate, then s is also known, and k is known, then s is also known. So this will be known. So this could be a linear model if s is this is all number, means this is not the function of any composition. Now if this k will depends on something, so let's say s, let's say this depends on the composition, then it could not be linear. Okay, then it will be non-linear model. Now compact matrix form, this we can write t, and this we can write x is equal to, this is b vector. So tx is equal to b. So this T is tri-diagonal matrix. If you see, this is tri-diagonal matrix. So it's a special form of matrix. So you can use the Gauss elimination, but by tri-diagonal matrix, this reduces Gauss elimination method to Thomas algorithm. Okay, tri-diagonal system, pentadiagonal system, it is used for that. So you can use that specialty for special matrices. Okay, this will reduce the effort. So x is the unknown vectors and b is the forcing vectors, means the inputs that you are giving known quantities. So tx is equal to b. Similarly, in the industry you will find many hundreds stages, okay, or 50, 60, 70 stages. So for that purpose we have t could be this, there is a live form, x could be this, and b could be this. Okay, so we have to develop the efficient algorithm for solving this matrix. This is also tri-diagonal matrix. So we will have to develop the efficient algorithm for solving such systems, and that we will develop later. Now another variation that you can do, suppose this t is dependent on s, okay, this x composition. So this x composition where t is the function of x, x is also function, x is unknown, so multiplied both are unknown. So this will be non-linear, tx by b. Okay, so what tx is equal to b, so s is also function of x, because k become function of x. So s will vary also with x, and t is dependent on s. Okay, t is dependent on x, so t will be the function of x. So both are unknowns, so we will use the iterative method. So if we will first guess the values of x, xi, we will calculate the k on the x based on the assumed value, and based on k we will calculate sx old, and hence we will calculate the tx old, because t will be dependent on the s, right? So then we will calculate. Now if this is known, then we can solve this tx old, x new that you have to calculate, and x old that you have put the as initial guess is equal to b. So tx is equal to b, so x new is equal to t inverse b. So t inverse b, you can calculate the x new, and this is the better guess, this will be the better guess, and you will continue till x new minus x old tends to 0, means they will both get close to each other, means they will both converge. Okay, third variation, if you change the specification, suppose change the specification means you are known with the y4 and y1, means suppose you have sulfur dioxide in the atmosphere, and you want to reduce the concentration of sulfur dioxide or carbon dioxide, then you are using the solvent to extract that. So you are using the solvent, so you are bringing the uy from y4 composition to y1 composition, and you know the vapor flow rate, means CO2 or SO2, whatever pollutants you want to remove from the atmosphere, and You also know the liquid composition at the inlet. Liquid composition, what should be the liquid composition at the inlet? You want to calculate the liquid flow rate. Suppose this is the I have changed the specification. This is let me bring you here. Suppose this vapor composition is known, inlet constant is y4 is known, b is known, and you know y1 also, how much change. You know x naught, but you don't know what is L. So you have to calculate the L, how much solvent, what must be the solvent flow rate to bring this change in the composition of gaseous pollutant, and hence to separate the gaseous pollutants. So here L become unknown, L become unknown. Now see, y is equal to kx, this is also linear, but the problem will become non-linear. How? See, L is unknown, so see this equation, L is unknown, so L is unknown, so S will be unknown. So S will be unknown, so this T matrix will depend on unknown. So this is unknown and this is unknown, and unknown multiplied, so you will get the non-linear equation. So if you slightly change the specification, you will get the non-linearity will come into picture. Now next third this is the variation, and next example that we can take reactor in series. So these are the reactors in series. Okay, F is the feed flow rate, and A naught is the inlet composition, then A1, then feed it to next reactor, ith reactor, this is ith reactor, and exit concentration is AI, and inlet concentration AI minus 1. Similarly for nth reactor, suppose capital N are the total number of reactors, An minus 1 is the inlet concentration, and An is the outlet concentration. So this AI, A1 to An are unknowns, okay, and A naught inlet composition is known, feed is known, and volume, reactor volume may be known or unknown. So suppose this is autocatalytic reactor, autocatalytic reaction. So unknowns are A1, A2, An, knowns are F, A naught, and B could be known, could be unknown. So let me take reactor volume is known. You have to get A1, A2 to An. So mass balance equation, you will write mass balance equation for each reactor, and phenomenological model, phenomenological model means do experiment to get the rate. So suppose rate you get R is equal to K, and reactor volume V, and AI concentration K square. So this is concentration is unknown, AI is unknown, so this is square of unknown, so this is non-linear model rate. Okay, you will combine both. So this is the rate of reaction, by that rate reactants or products are consumed or generated, and is equal to change in concentration AI minus 1 minus AI multiplied by feed flow rate. So this is, suppose letting beta is equal to kV by F, we have the following non-linear equation. So kV by F is equal to beta, so beta AI square is equal to AI minus 1 minus AI. Bring everything on the left hand side, be beta AI square plus AI minus 1 is equal to 0, I is equal to 1 to N. So this is you will get the N equation. So total variables are N plus 2 variables, because A naught to An is the N variable, and beta is the N, A naught to An, A1 to An, N variable, A naught, N plus 1 variable, beta, N plus 2 variable, total N plus 2 variable, N equation. So 2 degree of freedom you will have. So this is the non-linear equation, non-linearity due to AI square, and this is lumped S, and steady state model. Now let's take an example of lumped dynamic model. Suppose you have the molten metal, put it in this molten metal. Suppose this is you have put it in this crucible, and crucible have the temperature T2. This is ceramic material, and molten metal has the temperature T1. So molten metal is very hot, so it will cool down. So idea is to you have to cool it down, so you have to put the molten metal into the crucible. So to cool it means temperature will change with respect to time. Okay, now we will consider molten metal temperature is uniform everywhere, so this is lumped. Okay, because metal have high thermal conductivity, you can assume T1 is same everywhere, so T1 is uniform, but it may change with time. Now T2, if you can assume, so this at this point T2 and this point, you could assume that this is same, but at the inner wall of the crucible and the outer wall of the crucible, it will not be same, because heat will be radiated out to cool it down, the molten metal. Okay, heat will radiate it out. But we will take here also, we can assume that due to uniform lumped. Okay, but this is the biggest assumptions that we are taking, okay, in the model. So energy balance, you can assume this molten metal as a control volume, and you can take for other control volume like crucible only as a control volume. So if you are considering only molten metal as a control volume, so this is m on cp1 t1, that is the energy content. M on cp1 t1, that is the energy content in the molten metal, and rate of change of energy content would be d dt of m on cp1 t is equal to input, these molten metal not getting heat from anywhere, so this input is equal to 0 minus heat going out, means going out 1 to 2, means this from molten metal to crucible. So h1 a1, a1 is the interfacial area, h1 is the heat transfer coefficient, t1 minus t2, t1 minus t2, that's the temperature gradient driving force for the heat transfer. So heat loss from molten metal to crucible. So this is the equation, you will get differential equation. Second, energy balance on crucible, so you will apply to m2 cp2, t2 is the heat content, energy content of the crucible, so ddt of that. So h1 a1 t1 minus t2, this will be same because this is the heat loss from 1 to 2. So whatever heat lost by the molten metal will be gained by this ceramic crucible. Okay, so this is s1 a1 t1 minus t2 minus s2 a2 t2 minus t infinity, so lost to the surrounding. So this is t2 to t infinity, that is lost to the surrounding, so energy out. So this is the say two equation. So the above two equation can be represented using matrix notation, you can use. So d theta or dt, that's the t1 t2, that will depend on a theta is equal to a theta plus b. V is the forcing function, means known vectors, and a is the matrix of the numbers. So 2 cross 2, so this is a linear ODE, linear differential equation, and you must know the initial condition for this. So suppose Ti is the molten metal temperature and T infinity is the room temperature, whatever you are taking, for T2 is the crucible temperature, is the room temperature. So this is the lump dynamic model, dynamic because it is changing with respect to time, lumped because there is no spatial variation. So different types of model. So finally you have seen that you got the set of differential equations. So how to solve that set of differential equation, we will learn in this course, in this introduction to mathematical modeling for chemical engineer. We will learn all those things. Similarly, we will get at some places as a distributed model, you will get with a change with respect to space variable. So you will get either always differential equation, and if there is more than one variable, then you will get the partial differential. How to solve those, how to discretize that, what numerical methods we are going to use, we will discuss in the next lecture. Thank you.